Hi everyone, my name is David Klee, founder of Sequilibrium. Welcome to Module 11 of my course, the SQL Server on VMware Accelerator. We just wrapped up a good overview of the SQL Server instance and how to set it up best for virtual performance. Let's talk about how to engineer and maximize the performance of your virtual SQL Server workloads. This is the SQL Server Performance Tuning Module 11 of our SQL Server on VMware course. This module is a doozy. We're going to talk about how everything is shared in these virtual environments and the positive and negative impact of this sharing. We'll then move on to performance characterization through using Windows Perfmon to right-size the environment. Right-sizing is absolutely critical and about the most important thing that you can do for your virtual SQL servers. It impacts areas such as CPU scheduling and memory overcommitment ratios, both of which we're going to talk about in depth. We'll then talk about storage queuing, which is the next big problem with virtual environments. We'll talk about network throughput, but thankfully that one isn't that big of an issue. And then we'll talk about how to align all the layers to make sure the performance lines up to produce the best possible configuration. I've mentioned over and over again throughout this course, virtual platforms are possible because we have shared all of our compute resources. Now it's time to dig in and figure out how to micromanage our tuning to make sure the best possible micro and macro gains of performance occur. The performance killers that accompany mismanaged compute resources can be all over the place. All of these we're going to cover in depth. The very biggest challenge that I see is related to CPU overcommitment. It's not the act of overcommitting them itself. It's the act of trying to force the physical machine CPUs to do too much with too much context switching, all of which contributes to silent performance problems. Built-in defaults within VMware and the physical platform also destroy your storage latencies through significant queuing occurring within the hypervisor. Because your virtual machine admins probably don't understand why our SQL servers have such large memory footprints, memory pressure is still a concern, although not as big as it used to be. Virtual machine right-sizing is strictly science. Any art is strictly driven off of the numbers, not emotion or feeling or vendor recommendations. Our goal is to assign the correct number of compute resources, nothing more, nothing less, to maintain performance while minimizing the number of objects in our resource scheduling queue. By doing this, we reduce the number of objects in the queue and make the hypervisor schedulers more efficient. When we make them more efficient, we reduce the time spent in the queues. Less time spent in the queues means less time is essentially stolen from your virtual machine performance. We certainly need to maintain performance, but in many cases, assigning less virtual machine resources will actually improve performance. The days of throwing hardware at a performance problem are over. By micromanaging our resource allocations per workload, we're able to reduce the scheduling overhead and improve performance for our virtual machines. At the same time, we can increase the virtual machine density per physical machine. Squeezing more SQL servers onto the same physical machine while maintaining or improving performance means we potentially spend less on the expensive SQL Server licensing. We performed a massive right-sizing review for a major logistics company a couple of years back. In the business unit that we were in, we reviewed and right-sized 2,700 production SQL Server virtual machines. Their resource allocation standards were so overblown that we found we were able to right-size the virtual machines and double the virtual machine host density. It meant that we could turn off half of their SQL Server on VMware hardware, all while improving the performance of all of their critical production servers. Doing so reduced their SQL Server licensing footprint by 31 million USD. It goes back to improved management of our four main food groups: the processors, memory, storage, and network. Let's start with the processors. Processors are the most sensitive item in our entire environment to scheduling delays within the hypervisor, so let's define some key performance indicators to monitor the performance impact of our CPU overcommitment levels. Step number one is to determine the number of CPU cores needed on a given SQL server. This helps us understand the resource consumption of the available resources so that we can better allocate what is actually needed. Next is to determine how that CPU core count lines up with the physical machine CPU topology. Finally, we need to understand the prioritization of these workloads. If some virtual machines are arguably more important to the business than others, we can prioritize them in the hypervisor resource schedulers. Right-sizing our virtual machines not only means allocating the right amount of memory at the micro level, but making sure that we do not overcommit our memory at the host level. We have to give it the right amount of memory since a good amount of memory reduces our storage read demand. It's a really big balancing act to juggle the appropriate amount of memory to maintain performance and not offload reads onto the SAN all the time, but maintain virtual machine density on the host so that the hosts are not maxed out on memory, but their CPUs functionally idle. The single biggest thing that I stress is that we have a baseline of all of our critical SQL Server workloads. Not understanding the normal resource consumption of your virtual machines means we have no way to determine what it's consuming when things are running well. If we don't know what it's doing when it's running well, how can we ever understand what is wrong when something is running poorly? Let's figure out how to develop a resource consumption baseline. The foundation of a good baseline is a solid collection of actual performance metrics at the layer that we are interested in. We have to collect the performance metrics from all the layers to figure out how they correspond and correlate, but we can focus on a single layer to understand its perspective on what it's consuming. We have to distinguish the actual consumption patterns from the demand of your users rather than what the vendor claims is required to make their software run properly. Some third-party utilities claim to be able to generate a decent baseline. Some of them work quite well. I'm not going to list them off here because I'm not trying to sway or advertise for any of them, but if some of them have good enough coverage of all the key metrics, they can help you generate a baseline for many of the things that we care about. We'll start with the operating system level collection. Since most of you are running SQL Server on the Windows platform, we're going to focus on the Windows Perfmon layer as a foundation for collecting very granular information from all of your SQL Server instances in the underlying operating system so that we have this raw data that we can analyze. Many people use Perfmon and other tools to collect performance information just when there is a performance problem. I prefer to collect it around the clock and leave it running. Doing so helps us figure out what is going on a normal day. Having it running in the event that a performance issue occurs also gives us the ability to mine that information for root causes and the impact to the environment. Some third-party utilities do not collect significant performance information at a tight enough granularity, in my opinion, to provide meaningful insight. I prefer a 30-second granularity of collection. Anything more frequent than that may cause a noticeable performance penalty on the server being monitored, and that's no good at all. Anything too much higher than that means that if we have a short spike that interrupts service for a small period or random blips that occur, the law of averages may actually water down the data so that we might not detect the issue. I use Windows Perfmon in a rather specific manner, and I have a free PDF document that you can download to see exactly how I like to set it up. But rather than have you read through it, I'm going to show you here. You can use that document for reference when you go to set them up for your own servers, and it's attached to the next lesson. Now let's take a look at how to set Perfmon up for ongoing 24/7 collection. Let's open Perfmon. Hit Start, type the word Perfmon, and hit Enter. You've got monitoring tools and data collector sets. If you're looking for real-time information, select Performance Monitor. Otherwise, we're looking to set this up to collect 24/7. So expand data collector sets, user defined, and what we're going to do is we're going to create a new collector set. So right-click on user defined, select New, and then Data Collector Set. Type in a name here to identify it as yours. I'm going to put in my company name, HFX. We do want to create manually the counter set under Advanced. So here, Create Data Logs, select Performance Counter, and hit Next. We want our sample interval to be 30 seconds. We want this to be 30 seconds because anything more aggressive than that is going to be more overhead on the system. Anything less than that doesn't give us the granularity that we're really looking for with this sort of collection, and it's low overhead and doesn't take a lot of space. Click on Add for our performance counters. As you can see, there are a tremendous amount of counters that we can select from. For the full list of counters, see the document attached to this lesson that contains everything you need to know with the counters and a full printed guide for how to set this up. This is going to give you a PDF of all of the counters that we're looking for. If you want to click through and manually add these, go ahead and skip a little further into the video. Otherwise, we're going to walk through all the counters that you should select for basic SQL Server performance collection. Okay, first of all, it's under Processor. What we're going to do is select the things that we care about related to overall usage, processor usage by process, and processor usage by system kernel time. This is also listed here as privilege time. One big item to note, for every counter that we have, you're going to want to select all instances and not the underscore total that is there by default. Selecting all instances gives us every single item such as CPU number, hard disk by letter, things like that. Okay, next up, memory. Big thing here is available MB or megabytes. Note there are no instances for this selected counter. Some counters don't have instances. We also care about page faults per second, page reads per second, and page writes per second, and pages per second. Okay, for network adapter, we're interested in our packet outbound and received discards and errors. And these are really important because if there's networking issues either upstream or with inside this server, this can help us troubleshoot those items, as well as total bandwidth. Okay, for physical disk, we're going to look at percent idle time, average disk bytes per read and per write, average disk seconds per read and write, that's going to be storage latency once you convert it to milliseconds, average disk read and write queue length, disk bytes per second, read bytes per second, write bytes per second, and disk writes. Make sure again to select all instances. Next, paging file. We're very interested on what our paging file is actually doing. Next, percent of maximum frequency. Note this will also give us our Newman node as well as the per CPU total, and this tells us if we're power scaling any of the CPU cores. And then under processor information, processor queue length. It's an indication of internal CPU scheduling pressure. If you are on the VMware platform, we are interested in the active memory and the ballooned memory as well as swapped memory counters. Also, if you're on VMware, percent processor time and CPU stolen time are really important, as is effective VM speed in megahertz. That's the core counters for the Windows platform. Now, if you're running SQL Server, we have a number of other counters that we do want to go add here. If this is a default instance of SQL Server, you will see SQL Server : and then some level of counter. If it's a named instance, you're going to see MS SQL and then the instance name and then a colon and then the counter set and counter the instances. So if you have one or more instances on the machine that are named, make sure to check those out instead of looking for the regular ones. The full explanation for all of these counters will be found in an upcoming video. One interesting one to note here is batch response time grouped by milliseconds. It's really interesting. You can actually baseline your environment by these counters and see how things change with things like service packs and cumulative updates and Windows updates even. Buffer cache hit ratio under the buffer manager, as well as page life expectancy, free list stalls, page lookups, reads and writes, pretty important memory counters. Now under buffer node, database pages, local node, and remote node page lookups, as well as page life expectancy by Newman node. And transactions per second by database, which is our named instances here. Under general statistics, number of user connections and transactions per second are kind of important. Under latches, latch waits per second will give us a good idea of internal latching, and the next counter is locks, and same kind of thing. Batch request per second under SQL statistics, as well as compilations and recompilations, are also quite important. We are done adding the core counters. Go ahead and click Next. If you want to save these under a different location than the default, which is C drive, usually C drive, perflogs, HFX, and then whatever you name the collector, feel free to change a location here. I'm going to leave this as default for now. And click Next. Okay, right now we're going to save and close this. Our new counter is defined here. It's just not started yet. Okay, right-click on the collector, hit Properties. We do want to go tweak a few of these settings. Spot check to make sure the directory that you set is appropriate here. Usually these items are just fine in here. Now under Schedule, what we're looking to do is to start this every single day, and then we're going to recycle it at midnight. So under Schedule, we're going to start this at midnight. And then under our stop condition, because of some quirks within Windows, we're going to run this for 1 minute less than an entire day. So set the overall duration here to 1439 minutes. What this will do is stop itself about a minute shy of midnight and give it time to flush to disk, clear itself out, and then it'll restart right at midnight. On the right are our counters. If you right-click on the data collector and hit Properties, you'll see all of the counters selected, as well as a 30-second sample interval. Now under File, check your log file name. The file name format, we want to date stamp this. So YYYYMMDD, prefix this with a computer name in case you want to archive these off. And in case this thing gets interrupted in the middle of collection, we're going to append our log file. A little known feature here is that this thing can clean up after itself so it doesn't fill your hard drive up with data files that are just sitting there for months at a time. If you right-click on the collector, click Data Manager, and you'll note we can actually check how much free space we want to keep on the drive that you've selected. In this case, I'm selecting approximately 16 gigabytes minimum free, and our resource policy, every time this thing recycles, if we're going to run into space constraints, is to delete the oldest. Now, one good thing that we can do, we can also set this thing to create cab files, which are Microsoft's versions of compressed files. I don't want to say zips. And what we're going to do is we're going to create the cab file and delete the original data file after 7 days. Because I hope that we're going to be archiving these off somewhere else, we're going to have this thing after about 8 weeks go clean up itself. And that way it'll get rid of every trace on the file system. So set those and click OK. We're not quite done. Go back to Start and go Task Scheduler. This sounds a little weird, but you'll see why we need to do those. Expand Task Schedule Library, Microsoft, Windows, and go to PLA, because when I think Perfmon, I think PLA. You'll notice here under PLA, that's our Perfmon counter. So what's actually going on is this is a Windows scheduled task. Right-click on your counter and hit Properties. Triggers. You'll notice we have one for every single day at midnight, but we also want to have this thing start if the system turns on. So the scenario here is, let's say Sunday mornings, you're doing some routine patching before everybody gets up. The Perfmon collector may not turn on until midnight that night. If we set a system startup trigger to enable this, then life is good. It's going to turn on every single time that we start it up. So click on Triggers, click New. Now we want to begin the task at startup, and that's it. Click OK. There's one more thing we want to do here. Just in case, we want to make sure this thing doesn't run longer than a day. And if it's still running, we want to stop the existing instance. Go ahead and click OK. This is actually kind of important for scenarios where we have to do routine patching, maintenance, things like that that cause this thing to recycle on an abnormal period. Okay, we are done. Right-click on the counter and hit Start. You're now up and running. So if you go to the location where we told it to save the performance logs, in this case C drive, perflogs, admin, HFX, you'll notice there's individual folders and files there for each day. You may have to grant yourself permissions to get in there, no big deal. And there's our Perfmon file. Great. Everybody on the internet tells you to collect Perfmon information. Nobody tells you what to do with it. So stay tuned for a future video. I'm going to show you how to load these into a SQL Server database so that you can actually get to the raw data and start to mine the information for its value. I've just shown you how to set up ongoing Windows Perfmon for 24-hour-a-day ongoing collection. Feel free to customize this process as needed, since everyone's needs are different. The great thing is Windows Perfmon is completely free, and it's already on your Windows servers, and it is quite easy to set up and manage. The one thing Perfmon doesn't do is give you an easy way to review the contents of these Perfmon collections. Stay tuned for a follow-up video where I show you how to import the data into a Microsoft SQL Server database so that you can use the power of SQL Server and any other analytics tools you like to review this data and get to its true meaning. Everybody on the internet says how to set up Windows Perfmon. Nobody tells you what to do with it. Thankfully, we fixed this. If you go to the GitHub page on the screen, we have a PowerShell commandlet that you can use to load this raw Perfmon data into a SQL Server database for you to review with your favorite analytics tools. You can run this script nightly through Windows Scheduled Task or any other scheduling mechanism to reach out across your network and collect this data from a number of different servers. The data will be in a raw format, but this gives you the power to use your favorite analytics tools such as T-SQL, Power BI, SQL Server reporting services, or anything else to mine this data and form your own operational analysis. Let's take a look at this PowerShell script and how we can use this to import our data. Okay, now we want to go grab the PowerShell script. If you go out to github.com/heraflux/blg to SQL, you'll find not only the PowerShell script for how to do the import, but a handful of informational query samples that you can use to actually go set this up, as well as a database schema that we're going to use to set this up. You'll notice there's two schema files in there. One is for SQL Server 2016 and above, and the other is for previous versions other than SQL Server 2016. All you have to do, download the code and save it to a location on one of your machines, preferably not directly on your SQL Server, but something that has access to it. Okay, the very first thing that we need to do is to create a placeholder for where we're going to drop all of this data. Now, you may have a utility database or a stats database or some sort of working bucket for you to drop this into, but if you don't, we're just going to go ahead and create a database over here. So whatever your preferred method through the front end or T-SQL or however you want to do it, I'm just going to call this Perfmon Importer or Perfmon Import. Now, I'm a little picky. One of the things I really like to do is to auto-create incremental stats, auto-update stats asynchronously. I'll turn on Query Optimizer fixes, I'll allow snapshot isolation, and I will force isReadCommitted snapshot on. Now for this particular server, one of the things I am going to do is to turn on delayed durability. If you're not familiar with it, stay tuned for a future video. It's actually incredibly helpful for use cases like this, where you have the actual data and the operation is restartable or retryable. This can actually help speed things up. So in this case, we're going to do allowed. Now out on the GitHub page are a couple of functions and a simple little table for us to import into. So what I'm going to do is I'm going to take that script and I am going to import this into the new Perfmon import database that we just created. And you'll notice it's just a couple of functions that help you round dates to a particular certain time span, as well as our Perfmon import table. And you can see it's pretty simple. Got an identity value, server name, timestamp, counter set, counter name, counter instance, and our value. And now because this is SQL Server 2016 Service Pack 2 or above, in this case this is a 2019 instance, I'm going to use a clustered column store index instead of the usual primary key clustered index combo. There we go. Nice and simple. Our bucket is now created. Now that you have the file downloaded, go ahead and open up the blg to SQL.ps1 file. This is our main PowerShell script that we're going to execute. If you notice here, we have sample usage of this script. It's very simple. blg to SQL.ps1, perfmon directory, and then specify the location for that given server, and then the server name. Makes it really easy to go script out for multiple servers down the road. If you scroll down here, there are a handful of connection and target information details that you can pre-specify so you don't have to type it in each time. For this one, I've pre-specified the perfmon directory at the sample directory that I have on my desktop on this workstation. I have the server name of the machine that I'm profiling, and then a connection string here that's pointing over to a different machine with the initial catalog perfmon import. We do have specified the application name, so we know which application is actually doing the work. If you scroll down in here, you'll find that what it does is it checks to make sure the target directory that you specified is present, and then it goes through and does a check to make sure that we can connect to the SQL Server. If so, then we're good. Let's go ahead, and what it does is it unpacks all the cab files, which are kind of Microsoft and Perfmon's version of a zip file. It's just not quite as handy. It converts those, it extracts them, and then converts them to a tab-separated value format, TSV. The reason for this is a traditional CSV might actually break because there's a handful of the Perfmon counters themselves where the names contain a comma, and that actually breaks our standard. So once it's done exporting those back to a CSV name, but a TSV format right here, then it actually does a SQL Server bulk import directly into our target table. And you can see we're mapping the columns. I actually have a batch size here equal to what column store indexes are really preferring on inserts. We map our columns, and then for every record, we perform our insert, and then it cleans up afterwards. Scroll back up to the top here, and let's run this. Right now, you'll notice I have a folder on the file system here, perfmon data, And each one of these corresponds to a day's worth of Perfmon data in a folder. And this is what you're going to see on a normal output folder on a given server. So if we just double click into one, you'll notice I have the BLG file right here. I have the CSV file, or really it's a TSV file because I've run and tested this a few times, but that won't be there by normal. And then a report, and this is automatically created by Perfmon. So what this script is really going to do is it's going to iterate through each one of these, load the data into a database, and away we go. So if we hit run, it goes through and converts everything from BLGs to TSVs with a CSV name. And while this is running, we can actually go over to SQL Server, and I'm using Azure Data Studio for this one, and we can just do a count, and we can watch the information start to trickle in. Our import has completed. You'll notice we're back down to a command prompt here, and it looks like we imported a lot of data, but let's figure out exactly how much. Here's Azure Data Studio. You can use this or SQL Server Management Studio, whatever your method to connect into your SQL servers to start to run some diagnostic queries here. Okay, first of all, let's confirm how much data we actually imported. So if we look at our Perfmon import table, you can see this Perfmon data set contained 36 million data points. Not too shabby. If we take a look at the information that it imported, you can see we have an ID value, server name, date and time stamp down to every 30 seconds that we collected data. And then our counter set by process, processor, network adapter, things like that. Counter name, our instance name, and then our value. If we want to look at the entire time frame that we imported on this batch, because there was nothing else in this database, you can see here this was from April the 22nd to May the 6th. So it's a little over 2 weeks. So 30 million data points for that sounds like a lot, but it's actually pretty normal. This is at the point where any utility that you like Power BI, T-SQL, Excel, whatever you want to use, you can now get to this raw data to do whatever you want with for any sort of analytics that you care about. Now, out on GitHub, I do have a couple of sample scripts out there to give you an idea of what you can do. I'll show you a few of those right now. So first of all, I want to see the counters that are actually available to us in the system. So this query right here will give you all counters for this particular server. Counter set, counter instance. So memory available M bytes, there's no instances for this one. Or physical disk, average disk bytes per read, things like that. Pretty handy. Now we have a sense for what are we actually working with here. The next query will go and grab a certain counter. In this case, I have it defined up here. This way you can do this as a rolling drop down in your reporting tool, however you want to do it. So you specify the counter set and counter, and then it goes through and it's going to grab us every one of those values. So you can see server name, date and timestamp, and this is CPU consumption by CPU core. In this case, this was a 16-core SQL server. CPU core numbers 0 to 15. Here's our counter value. Once we get past the first seed, you can see we've got some activity in there. Not too bad. It gives us the raw data, and now we can do something with it. If we want to do a little bit more advanced, we can actually do the same thing. So same counter. I want to see the average counter. Now I can run it like this. So you can see for every time sample that we now have our average counter value across all cores. The tough part with this is that it doesn't always do it justice. What if, let's say this on the 16-core SQL Server, 2 CPUs were going berserk and the rest were functionally idle? That can happen. With that information, what we end up getting is a skew, or we kind of average out the meaning of the data. In this case, we have a good solid number here. It doesn't tell us what those individual cores were doing. The next query here is designed to fix this. What it does is it's going to give us all of the instances for a given counter and then put them in the order of which we care about. In this case, it's CPUs, so they're in the order of the CPUs. We have to do a little bit of work here to get them into order, and we're actually going to be building a dynamic pivot table inside SQL Server to do this. But with this information comes a lot of power. Check this out. So I'm running this, and now you can actually see the date and timestamp, and now CPU 0, CPU 1, CPU 2. And we have our individual metrics all laid out right here. Pretty darn handy. Because now here's our analytics, and now we can do something about this. We can do something with it. And it's in a nice, easy to consume format that dynamically adjusts because not all of your same servers are going to have the same CPU count. Awesome. Now you know how to get to the data. It's in a raw format, and we can do something about it. Now you can schedule this to run every night. You can adjust Perfmon to start to compress after a given day, and you can turn around and import this nightly. And now you can start to build a data warehouse of your performance information. And that is absolutely critical to figuring out not just what happened yesterday when there was a problem, but day by day trends that really do matter depending on what's going on in your environment. Maybe license management, maybe you're interested in looking at the cloud and you want to figure out how big to size your cloud objects. All of these things you can do once you get the raw data. Now, before you start diving into the data, we need to figure out what we're actually analyzing for. First of all, is our business a 24/7 around-the-clock business? Or is it more Monday to Friday, 8 a.m. to 5 p.m.? Do we have certain key windows of time where nightly processes occur each evening and have to run within a certain time span? Do we have maintenance windows that occur outside of business hours each night or each week? How long do these tasks normally take? What other routine processes do we have running each day, each night, or over the weekend? What if we want to hone in on certain days of the week or months of the year? Do we have time periods where the business is certainly busier than the others? We have some clients in the heating and air business that are extremely busy in the fall and in the spring. These systems are really quiet during the middle of the winter and in the middle of the summer because people have already done most of the work to prepare their homes and businesses for the upcoming season. What are some of these time spans that are very sensitive to the run times of the tasks in them? Do any of these things need to run within that certain time span? The reason I bring all of this up is because if I have an 8-hour window to run index maintenance and integrity checks in, and my CPU spike almost to max for just 30 minutes, does it really matter if they take a few more minutes to run? In some cases, yes, and in some cases, no. If the high point of my CPU consumption during a normal week is in the middle of these maintenance windows in the middle of the night, are they safe to ignore? Maybe not ignore, but they may be appropriate to simply watch out to make sure that the runtimes don't grow considerably over time. The other reason to watch out for these is that if our consumption spikes at the same time for all the virtual machines on the same host, we may tend to start to stack up our resource scheduling queues and cause performance issues. If we can attempt to stagger these tasks, we can maintain performance and improve interoperability between the virtual machines. Take a look at this Perfmon output from one of my systems. You can see that we have a CPU spike at 4 a.m. with a certain nightly process that runs then. During normal business hours, however, our CPU consumption barely breaks 30%. You can also see a sharp drop-off when some people leave work at 4 p.m. and everyone else goes home by 5:30. If I'm just focused on my maximums, that spike at 4 a.m. could cause us some alarm. Because I know that this is a routine maintenance window that I can shuffle around to a different point in time, and the fact that I have at least 2 hours for it to complete before people start coming to work that day, it makes me rest easy that I can safely put that spike on the back burner and simply keep an eye on it. Our resource consumption patterns can also vary quite differently between a normal business week and the weekends. You can see in this screenshot we had a customer that ran integrity checks and index maintenance early Saturday and Sunday mornings. They had a nightly process that ran Sunday night to Thursday night at 5 a.m. each night. The resource consumption patterns are somewhat different between the two time spans. Let's take a little closer look at that original Perfmon output. This is a CPU by core output covering a full 5-day Monday to Friday review. If we start at midnight, we have something that has started running just after midnight that runs approximately 30 minutes. There's a single-threaded application or something running at approximately 1:30 a.m. There's a big spike across all cores at 4 a.m. for approximately 10 to 15 minutes. Starting at 7 a.m., you have a normal business activity through the day, with a small decrease while staff go to lunch. There's a sharp drop-off at approximately 4:15 when one of their shifts ends for the day, and then you see everybody else that tends to leave by about 6 p.m. There's one small process that's running at approximately 9:30 p.m., and after that, the day pattern repeats. You can see just how much time we have remaining after that 4 a.m. process runs before the normal business day starts. We start to understand what we can gather in terms of CPU consumption. Now let's take a really good look at analyzing this data so we can figure out just how many CPU cores we actually need. This is one example of a virtual machine that was sized way too high for its actual consumption. This is a 12-core virtual machine, and you can see that this thing was barely even breathing. A different process at 4 a.m. on this machine was consuming one CPU core for an hour and a half, but that process was almost entirely single-threaded. We have one CPU core that is slightly higher than the others around the clock. That one's probably handling either storage access or network traffic. This machine is so resource overallocated it's not even funny. After a little bit of inquiry, the customer told me that it was a database server underneath one of their websites. They had no idea how much it would actually consume, so they simply bought more than they figured they would need. In this case, it was SQL Server Standard Edition, but they still spent a lot more than they actually needed. They should have started small and witnessed what that machine was doing during initial testing. Let's take a different example. This particular server was underneath a manufacturing organization that was largely an 8 to 5 shop. It was another 12-core SQL Server that had some moderate activity throughout the day. Because they're mostly normal business hours, break out the two windows of time. Highlighted in white is a normal stretch of operational time from approximately 7:30 a.m. to 7 p.m. Outside of that is highlighted in red. If we look at our CPU consumption during normal business hours, we can see that the absolute peak on a single core is no more than about 38% just before lunch. Most of the cores are hovering in the 10 to 25% range. If we look at after hours, there is a big burst of activity at 1 a.m. that is consuming all the CPU cores. It's still not that busy, but it's certainly active during that period of time. They have some overnight processes that start at about 3 a.m. and they're finished by 5 a.m. There are some other processes that run every hour on the 30 minutes of the hour that do take some time. The reason I bring this up is so that we can understand the operational signature of our CPU consumption for this machine. Realistically, this machine would have been quite comfortable between 6 and 8 virtual CPUs. Here's a different pattern altogether. This particular server was sending out high CPU alerts during business hours. After getting a really good sense for what was actually occurring, it looks like the process they were running every hour was running single-threaded. One CPU core was pushing between 60 and 72% busy for the time span that this process was running. The customer was asking if they should add more CPUs to make the process faster. A really quick look at our CPU consumption by core shows that no matter how many CPUs they have on this machine, the process will never utilize more than one. We were actually able to downsize the server to just 4 cores, and it probably would have run fine on just 2. This was also a SQL Server Standard Edition machine, and since the minimum purchase for licensing is 4 cores, they decided to keep it at 4. Let's take a look at the other extreme. This particular SQL Server has 8 CPU cores and was absolutely destroyed by inefficient third-party software code through normal business hours. All 8 cores were so pressured on CPU that the business was suffering significant performance issues during normal business hours. As a short-term fix, while we worked with a third-party application vendor, they increased the core count to 16. It relieved the pressure a little bit, but was still immediately consuming all 16 in the process. We started digging in, and with some strategic index tuning, we got it to just 75% busy during business hours on 8 cores. We then worked with the application vendor to reduce the frequency of some polling activity within the application, and we were able to cut this down to 30% busy on just 8 cores. Once we get a sense for our operational patterns, now it's time to figure out how many cores do we actually need. First of all, we want to right-size our core count and then make sure it aligns with their physical CPU topology. Understanding what our current consumption rates are during the business hours and days of the week that matter to us helps us determine what we actually need. Add the appropriate amount of headroom for variance in user patterns and growth, of course. I usually say in the 20% range. Keep in mind that because these are virtual machines, you can expand the resource allocation up to what the entire host contains with just a small outage window. Let's allocate what we actually need right now. Once we understand what we need right now we can figure out if this core count is aligned with the physical machine NUMA topology or if we need to do anything fancy to force it to align. Take the example of a new virtual machine on a 24-core physical machine. If the virtual machine CPU core count is less than or equal to the number of cores in one physical socket, create the virtual machine with just one socket and with that number of cores. If for whatever reason the virtual machine CPU count is greater than the number of cores that exist in one physical machine socket, split the virtual machine down the middle and compare again. The example on the screen shows a 16-core virtual machine. 16 is greater than 12, so build a virtual machine for 2 virtual sockets, each with 8 cores. The hypervisor will do its best to make sure that these land on the corresponding physical NUMA nodes, and your SQL Server will be aware of this split so that it can perform memory management more efficiently. For SQL Server and other NUMA-aware workloads, virtual machine NUMA matters just as much as physical machine NUMA alignment. I'll show you a really weird example of how these might create your perfect storm. I set up Perfmon on this SQL Server at this customer's environment. It was a 16-core SQL Server. The very first thing that I asked them is, what are your normal business hours? And they told me it's a normal 8 a.m. to 5 p.m. Monday to Friday organization. The CPU consumption patterns on this machine told me that something was a little abnormal. If you look at this percentile analysis, it shows the graphs are minimum, average, and maximum percentiles over each 15-minute time slice of the day, as well as the 50th, 95th, and 99th percentile in there. The grouping was incredibly tight, which is not normal for SQL Server workloads. Take a look at the breakout between our Windows system consumption and our user process consumption. Our system time was hovering between 32 and 38%. I raise a red flag when that percentage stays at over just 10%. Something was seriously wrong with this machine. Now let's look at the per core breakout. What in the deuce is going on? Half of the cores are hovering between 55 and 88% busy around the clock. The other half were barely being used or just a little bit active, but certainly not evenly distributed. Given that the system should only be busy during normal business hours, this is extremely unusual. Let's use another little-known Perfmon counter to double-check something. There's a Perfmon counter called processor information % of maximum frequency. When you look at the Perfmon counter name itself in the Perfmon output, there is a processor information with underscore total in the name. The other counters all start with a number. This number corresponds to the actual NUMA node ID and guest. This virtual machine had been constructed with 8 NUMA nodes, each with 2 cores per socket. The physical server that this was running on was a 2-socket, 8-core physical server. Both SQL Server and the Windows operating system have some very interesting licensing limitations when running on Standard Edition. Both SQL Server and Windows Standard Edition have a limit of 24 CPU cores or 4 CPU sockets, whichever is lower. Think about that for a minute. The virtual machine was built for 8 virtual sockets. Windows and SQL Server were both unable to address all of the presented CPU sockets. The reason the CPU consumption was so high on 8 of the CPUs was that Windows and SQL Server were not agreeing on which CPUs they could actually use. The context switching which may occur inside the Windows layer from this disagreement was so high that 8 CPUs were absolutely destroyed while it was arguing with itself. Take a look at the heat map of the CPU consumption on this machine. By the way, this is actually really easy to generate within Excel with the conditional color chart option. You can see very clearly that only a subset of the CPUs were actually being used, and of what was being used, it certainly wasn't evenly distributed. Let's fix this. We took the next available maintenance window, which in this case was an emergency maintenance window that night, and shut the virtual machine down. We reconfigured the virtual machine for 1 CPU socket and just 8 CPU cores. That's right, we cut the core count in half since we proved that SQL Server itself didn't need all 16. We powered the SQL Server back on and let it run for the next few days while monitoring its performance with Perfmon. What you see here is how the SQL Server responded. Starting at 7 a.m., a lot of people got to work and hit the system, and you can see an appropriate response of CPU consumption up to about 38% on 1 core. There's a process running at noon on just 1 core. There's also a really long running process that we found that starts at 5 p.m. with another one kicking in at 9 p.m. Both of those ran single-threaded again. Because of how our CPUs stopped fighting themselves and started working together, our peak CPU consumption across all cores was barely 25% during business hours. Also, our actual net SQL Server performance gain was 3.5 times faster for all important reports and processes. Because of these performance gains, we actually downsized the SQL Server again to just 4 cores. Because they'd already paid for the licensing, we repurposed that licensing to build a reporting server where we backed up the production database nightly and restored it, as well as save them on licensing for a new SQL Server environment on an upcoming project. Okay, now we have a good understanding of how many CPUs we should have on our machines. Now let's figure out the net impact of these CPUs in my virtual environment. I talked a lot about CPU sizing and everything related to it. Let's take a really good look now at what VMware has to offer for metrics around monitoring and managing our scheduling delays. Anything that we can do to better manage these delays means we get better performance. When you think you execute a query and it runs on the CPUs, it looks just like it's running like normal. The guest operating system has no idea that it's actually inside a virtual machine, but there's more to it than meets the eye. When you execute that query, there is a little bit of time taken to place that command onto the virtual CPU scheduling queues. Then, based on how much activity is actually going on in the physical machine, there's time spent in the queue called the ready queue. The total time spent between these two steps is called %ready time. Finally, the hypervisor has allowed this process to start processing and it begins to run. However, it may not finish to the end immediately. It may get interrupted. When it gets interrupted, there are multiple states that it can persist in. It can go back into a ready state. It can also go into a kernel wait state. It may also go through a state called co-stop, and we'll spend more time on that shortly. Throughout this entire period, it starts and stops, but then proceeds on. Throughout this entire process, there could also be physical machine efficiency losses through things like hyperthreading and physical CPU power savings. This sounds like a very crazy and complex process that could have a high amount of overhead no matter what. Thankfully, VMware and most other modern hypervisors have a very low overhead for this entire process. When our hypervisor CPU scheduling is managed properly, this entire process is usually less than 0.25% overhead. I find that to be incredibly advantageous. However, when these queues are managed incorrectly or inefficiently, this delay can be hundreds of percent overhead, which is never good for performance. Thankfully, VMware has some of the best metrics to help us measure and monitor these queues on an ongoing basis. Some of these can be early indicators of CPU scheduling potential pressure. Others are more real-time metrics, but can be analyzed to figure out the net impact. The primary metric that I care about is called CPU ready. The next is called CPU co-stop. Finally, there are a couple called demand and entitlement, and I love to compare them. Let's dive into these metrics and figure out how to interpret them. All of the metrics that I care about have different polling intervals inside VMware. The intervals that VMs collect our information in real time can be past day, past week, past month, and past year. Remember when I previously said that the default collection metrics for the vCenter performance statistics are set too low? At this point, you should verify that those collection metrics have been increased. We want to make sure that we have all the data that we care about, not the subset that is displayed with the default collection levels. The real-time interval that you see when you access a virtual machine or a host is the past hour of key metrics measured in a 20-second polling interval. Believe it or not, these metrics are not actually stored inside the vCenter database yet. When you access the real-time statistics, you're fetching them directly from the host memory and not actually the vCenter. At the 1 hour mark, VMware rolls up into a 5-minute rolling interval and then stores some of the information into the vCenter database. The rest, it simply throws out. The next view is the past day view. It shows the full previous day on a 5-minute granularity. Some of these metrics can actually be summation metrics, and some are averages across those 5-minute intervals. I'll show you examples of each of these soon. We then move to the past week view, which is a 30-minute aggregation. At this point, the data is so watered down through the law of averages that I generally find it unusable. Our first metric is called CPU ready. This is my first and primary go-to metric when reviewing virtual machine performance overhead. It's a measurement of the total number of milliseconds that a virtual machine CPU has spent in the ready-to-run state across the default polling interval of 20 seconds. It's the time wasted that the virtual machine is not actually executing at what you want while it waits in the queue. Analyzing this information can be indicative of significant performance challenges that are hard to detect from inside the virtual machine. It can also help show us if we have multiple CPU processing imbalances across the host. Some counters for this metric show the individual CPU scheduling delays. Some show the sum of the ready time across all of the cores in the virtual machine. Let's take a good look at what this actually looks like. If you go to your virtual machine, go to VM, Monitor, Performance, Advanced, and then under the view, you should see something called CPU ready. You can also find it if you go under Chart Options and look for CPU metrics. This metric is a summation metric. Like I mentioned a minute ago, it's measurable across the individual cores as well as the sum across all cores. It's the number of milliseconds spent in the queue on a 20-second polling interval in the real-time view. You can convert this to a percentage to understand the percent performance hit. In the real-time view, the individual calculation is pretty straightforward. If you're looking at the individual CPU core itself, you can see this in the chart by the CPU number. Take that value and divide it by 20 seconds and then by 1000 milliseconds per second. If you're looking for the average impact across all cores, take the sum value for the cores, divide it by the number of CPUs, then divide by 20 seconds and then 1000 milliseconds per second. If you do the calculation on this, in the screenshot here, you can see the worst individual core over the last hour has 63 milliseconds at worst and across all cores at 160. If you use these calculations, you'll find that in this screenshot, the worst performance hit on an individual CPU core was just 0.315%. The worst impact across all CPU cores in the last hour was just 0.2%. Those are phenomenal numbers, and usually what I find on normal production environments with just a small amount of acceptable CPU overcommitment. For real-time view, if you want VMware to do the percentage calculation for you, instead of selecting ready, select readiness. If you go to the chart options under the CPU counters, select CPU readiness. This is the percent performance hit. It's just harder to view this one because the chart's based on a 100 scale, and if you have a CPU scheduling penalty high enough to actually show up as a line on this counter, you're doing it completely wrong. I generally like to look at the ready time instead and do my own calculations. Well, that was just our real-time view. If you go to the past day view, you'll find that the numbers look a lot higher than in the real-time view. That's because this is still a summation view. What VMware has done is taken all of the data points collected in a 5-minute rollup interval and added them together. You can do the same sort of calculations, but divide by 15. In the 5-minute rollup window, there are 15 20-second polling intervals in that time span that it adds together. You now end up with the same perspective after doing this little adjustment. Remember now that the average over a 5-minute interval is what we're looking at instead of the prior 20-second interval. There are a lot of different reasons for elevated CPU ready times. The reasons are always varied, but I use this as both an early warning symptom of potential issues and an easy indicator of current challenges. It could be that your virtual machine NUMA is imbalanced with the physical machine NUMA topology. If the hypervisor has a very active physical NUMA node, you might find that the virtual machine CPU ready time for the virtual CPUs on that physical NUMA node might be a lot higher than the ones on the other node. There could also be a very high amount of context switching occurring in both the hypervisor and in the physical machine layers. It could be that the hypervisor is moving the NUMA home node across sockets, context switching from attempting to leverage hyperthreaded cores, power savings, or core parking on the physical machine CPUs, or processor cluster on die management could all be impacting this. This was part of the reason why we spend so much time on right-sizing our virtual machines so that we can minimize the number of objects placed into the queues. It could also be that there's just simply too much going on these physical CPUs. There just might be too much activity inside all the virtual machines on the host, and some of the virtual machines may end up getting squeezed as a result. Okay, now let's take a look at CPU ready. So go ahead and log back into vCenter, find your SQL Server virtual machine, go to Monitor, Performance, Advanced. Now go to Chart Options. Under CPU, hit this little square so that we unselect everything. Check Ready. Now we have the machine and the CPUs selected. Here's your CPU ready time from a live environment. You can see this is the number of milliseconds every 20 seconds in the real-time view by virtual CPU and added together for the machine name. As you can see, let's go ahead and start up Windows Calculator here. Let's do the math. Let's take the worst per core number, 17 milliseconds, 20,000 divided by, multiply it by 100 to convert it to a percent. That's 0.085% performance penalty. This is on a host with about 25 other virtual machines. That's fantastic. That's exactly what I want to see. Now let's switch gears to co-stop. Think of it this way. The individual virtual machine CPUs on a virtual machine with a lot of virtual CPUs have to be managed by the hypervisor. However, the operating system expects these cores to be in sync as it's built for a physical machine platform and doesn't know that it's virtual. The hypervisor scheduling queues are not always going to be lined up exactly for each of the virtual CPUs. If one of the virtual CPUs gets a little further ahead in the hypervisor CPU scheduling queues, it could cause a pretty serious problem inside the virtual machine. Thankfully, VMware does a really good job of detecting this and will actually pause one or more of the virtual machines in the queues to let the others catch up. The amount of time spent paused is called CPU co-stop. It's also measured in milliseconds per polling interval, similar to CPU ready time. In order to review co-stop, we need to dig into the virtual machine statistics a little deeper. Go back to that virtual machine, click Monitor, then Performance, Advanced, and then select the CPU co-stop counter and hit OK. It's a summation metric just like ready time, and you'll see the same total for all CPUs and the individual CPU cores presented in the charts. Unlike ready time, do not convert this to a percent. The warning signs that I'm looking for on this screen are pretty straightforward. An occasional little ripple is perfectly normal. However, if I see a lot of CPU co-stop together in really large spikes, or if I see sustained co-stop values over a lengthy period of time, I know that I have a massive performance penalty and that I want to investigate that immediately. Just like with ready time, there are a lot of reasons for CPU co-stop that are fairly familiar. We have the same vNUMA imbalances, lots of context switching, and too much activity on the host. We also have a state where co-stop can be elevated if a virtual machine snapshot is present on this machine. This is a little-known activity that most virtual machine administrators are not aware of. The act of placing the snapshot on the virtual machine itself will not trigger co-stop, but as the snapshot delta disks grow, the amount of co-stop can increase over time. This is part of the reason why I say use snapshots effectively when it's the right use case, but make sure you remove them from the virtual machine as soon as you're done with them. Let's take a look at CoStop in a live environment with a lot of virtual machine activity. Okay, go back to your virtual machine. Now let's go over to Monitor, Performance, Advanced. Go up to under Chart Options, make sure you have CPU selected. Click that to deselect everything. Now check CoStop. In the last hour, we have had one little wiggle of 10 milliseconds on just one CPU. That is perfectly acceptable. That's what I want to see. Where you get into trouble here is if you see things that are really, really high on a lot of cores or sustained over a period of time. Don't convert this to a percent. Any of those scenarios where they're either long-ranged or really, really high, those are surefire ways to detect substantial performance hits, and that's when you need to go talk to your virtual machine administrators. Your virtual machine configuration can really hurt your CPU scheduling times. Some virtual machine administrators will set megahertz limits or share values on your virtual machines as part of their configuration. I don't like to do either of these, as this is micromanaging a macro level issue. It also means that these settings can go overlooked when you're performance troubleshooting. If you see any of these on your virtual machines, go ask your virtual machine administrators why these are there and see if you can remove them. Believe it or not, VMware does a very good job of sneaking in a little-known Perfmon counter that will give us an approximation of the performance penalty from a combination of CPU ready time, CPU co-stop, and VMware kernel time. There are two Perfmon counter sets that are added with the VMware Tools package called VM Processor and VM Memory. Under the VM Processor counter set is a counter called CPU Stolen. If you track this counter with Perfmon and then convert it to a percent, you'll see the approximated CPU scheduling time on the VM. It's amazing that VMware provides this counter in guest, as no other hypervisors give you this level of information inside the virtual machine. You can track this with any of your favorite third-party monitoring tools and can trigger alerts. My personal thresholds are that a warning threshold should be 2.5% and an alerting threshold at 3.5%. The rough impact inside the virtual machine for SQL Server, since some things go parallel while others go single-threaded, is about double this value. At 2.5% gross or 5% net, that's low enough where I claim there's a high likelihood that your workloads and your users won't notice. At 3.5% gross, that's 7% net. Most likely your users won't notice at this point, but if it gets any worse than that, your power users will start to notice and probably pick up the phone to complain. Being in IT for this long, that's the last thing that we want. So keep it under this threshold and keep the users happy. The next set of counters are demand and entitlement. If you go into the performance properties for your VM, you'll see both entitlement and demand. Entitlement is if every virtual machine on the host were using 100% of its available CPU, this is the megahertz available for this virtual machine to use. Demand is the actual megahertz requested from inside the workload inside the virtual machine. Most of the time, demand will be lower than entitlement and everything's okay. However, if demand is greater than entitlement, it's an early indicator of possible CPU scheduling pressure with its associated performance penalties. You'll find that demand can cross entitlement during periods of heavy CPU scheduling activity. It's your canary in a coal mine, so to speak. The higher and longer that demand is higher than entitlement, the higher probability that you'll start experiencing elevated CPU ready and co-stop scheduling times. There's also a counter called demand versus entitlement ratio, but I prefer to see both stacked for a more appealing visual. Let's take a look at a live environment for demand versus entitlement ratios. Okay, go back to your virtual machine, go to Monitor, Performance, Advanced, Real-Time Chart Options. Under CPU, deselect whatever's selected in there and then select both demand and entitlement. Hit OK. The black line on the top is the entitlement. The blue line on the bottom is demand. In this case, demand is far lower than entitlement. So that's part of the reason why we see really good CPU ready and co-stop times on this particular virtual machine. We have no significant performance penalties related to CPU scheduling whatsoever. It is incredibly important to track and trend these key metrics, and for more reasons than are apparent. Think about this. If a virtual machine CPUs are being slowed down by a considerable margin each hour, that's a decent amount of time that is effectively lost inside the virtual machine. Think of an analog wristwatch with a battery that's about to fail. It starts to run slower and slower, and at the end of the day, it could be a few minutes or maybe longer behind. Whenever Active Directory resyncs the ingest time from the NTP server, the time inside the virtual machine leaps ahead. It might actually jump over a milestone like an agent job start time or a Windows Server failover cluster health check. All of these scenarios are quite horrible if the time sync spread is too high. They call this process clock drift. I've seen this break a SQL Server high availability solution. If the clock gets too far apart between the members of the HA feature, Active Directory could cause one or more of the members to be kicked out. It can also skew your Perfmon metrics inside the virtual machine. Usually it's not that bad, but if the host CPU scheduling pressure is really bad, you can start to see your disk latency rates increase, as well as certain SQL Server wait types around CPU and memory management start to rise. There are ways where you can look at the metrics on a host for all of the virtual machines together. By default, the CPU and other views of this host are pretty useless when trying to see all the activity. The host-level metric views have been hidden in plain sight for a long time now. There's a chart type called Stacked Graph by VM that allows you to pick a single metric and display a stacked line graph for all the virtual machines on the host. Just make sure to deselect the host from the list of objects so that you don't get double the metrics. You can get there by picking a host, going to Monitor, Performance, Advanced, Chart Options, CPU, Chart Type, and then selecting Stacked Graph by VM. Pick a single metric like CPU usage in megahertz. You end up with a chart like this. It's fantastic that you can now visually see all the VM activity in one spot on that host. Unfortunately, you can't go beyond the single host at this point in time, but this is a pretty good start for what you get. You can see when one VM spikes for certain in-guest operations like CPU or storage consumption. You can also do other metrics like CPU ready or readiness, storage throughput, network traffic, or anything else that VMware tracks. It's amazing to see this at a macro level per host. It's even got an option on the screen to export the image to a JPEG so that you can store it and share it. The best part is that you can look quickly by host for all VMs that might have high CPU ready times or co-stop values. It'll save you a lot of time if you're doing a platform health check. Let's jump to virtual machine memory sizing. There are no counters at the Windows or Linux base layer that will give us a good metric on what SQL Server is doing with the buffer pool. That's self-contained within the SQL Server engine, and the internal usage of that memory is not shared with the underlying operating system. We have to turn on SQL Server memory counters per instance. Thankfully, many of these can be captured with the instance-specific counters that are available in Windows Perfmon. There's no single counter that captures everything that SQL Server is doing with memory, period. I want to get as many of the important counters that we can to produce a better picture of how the memory is being used. SQL Server's buffer cache hit ratio is one such counter. It gives us a good idea if we have enough memory to hold and store commonly accessed objects and data. Normally, we'll have this value well over 99% through normal business hours. It might drop when memory is flushed out, such as during backups or index maintenance, but that should pop right back up when those processes are done. Another is page life expectancy by Numanode. Page life expectancy, or PLE, is a measurement of the approximate time in seconds that a normal page of data stays in the SQL Server buffer pool before it gets pushed out to make room for more warm data. Some internet sources, and you can trust everything on the internet, have the magic number at 300. That's bogus. I claim that it's pretty dependent on your workload and how you're using the platform. I personally want to see PLE above a few thousand during business hours for regular OLTP systems. This can change depending on the platform. If there are large reports, queries with high memory grants, backups occurring in the middle of the day, etc., your PLE profile can be quite variable. The chart on the screen shows how a process kicked off and ran for a bit of time each day reduced the PLE a little until it was completed. Once it finished, nothing was running that needed SQL Server to push a lot of data out of the buffer pool to make room for more active data, so the PLE will climb right back up as the data would stay put for longer. But it depends on how you're using it and the speed of the platform underneath. If your storage subsystem can keep up with the storage read demands, what if you can reduce your SQL Server memory in the buffer pool by a small margin? The next PLE chart shows what happens if your memory allocation is a bit lower than we like. This server kept PLE quite low and was smacking 0 throughout the entire business day. The read demand from storage was quite high, and their storage subsystem was struggling to keep up. We had them add about 64 gigs of RAM to the VM to up the memory footprint, and immediately SQL Server got happier. Remember that SQL Server memory is basically a storage-level read cache. Working set data gets stored here as an assumption from Microsoft that volatile RAM is faster than non-volatile storage. RAM is your read cache. If you have a low amount of RAM, you could potentially be reading a lot of the same data over and over again from your storage subsystem. Lots of RAM, on the other hand, means that you could be holding all working set data in memory for days at a time without ever needing to drop to disk at all. If your page life expectancy is measured in days or weeks, there is a chance that you could reduce your memory footprint by incremental steps. Test and retest. You'd be surprised that you might not need all of the memory that you have while keeping performance where you need it. Remember, the larger the memory footprint, the smaller the number of SQL Server VMs that we can put on the same host. If we can decrease the VM's memory size by a small margin and keep performance solid, we can probably put a few other SQL servers on the same host. Do that a few times and there's a chance that we can reduce the number of hosts that we actually need. You know how expensive the host and the SQL Server licensing actually are. Think about how much capital expense you can save. You have the ability to set these at the SQL Server instance level. There are two options, minimum memory and maximum memory, that define the bounds for the SQL Server buffer pool. Can faster storage help you reduce your memory footprint? What happens to your key memory usage metrics if you take a gig or two off the maximum setting? Test and validate, because every bit saved can make the server faster and improve your VM density at the same time. Let's talk about some key metrics that we can use to help gauge how much memory pressure the virtual machine is under. I've stressed over the entire course that you should always maintain zero memory pressure on the host, period. There should be no memory overcommitment for your SQL Server VMs. You can use a stack graph by VM with a consumed memory counter to see the memory footprint consumed by each VM of the host. Take some time and review your largest memory consumers. It's gonna be the SQL servers, and you might do some testing to validate that you could possibly maintain performance without quite as large of a memory footprint. Do not start to hurt performance by taking too much away, of course, but you can do some functional testing by shaving off a few gigs here and there and see how the system responds. Your Perfmon data gives you a great way to do the baseline. VMware has the active memory counter. It's what VMware thinks is being used by the applications inside the virtual machine. Your VM administrators are told by VMware that this is the counter that they should use to determine how much memory is being used and if there's too much or not enough memory assigned to the virtual machine. Unfortunately, this counter is incredibly inaccurate for SQL servers and other applications that do their own application-level memory management. SQL Server and other applications shield what they do from the underlying operating system, especially how it uses it as a storage read cache. As a result, the active memory counter is simply not accurate to gauge the amount of memory that a SQL Server virtual machine is actually using. Because the SQL Server buffer pool doesn't change contents that fast, active memory counter will actually show a lower value for your SQL servers, leading them to believe that you're not using all the RAM. The SQL Server level metrics can confirm if you're actually fully using the memory. Your virtual machine administrators might argue with you on this point. Feel free to point them to the SQL Server on VMware Best Practices Guide over at vmware.com. I know this statement is in there to back this up because I put it in there. The alternative counter is to use the consumed memory counter. We can safely assume that a SQL Server's buffer pool is going to use just about all the memory that you grant it, and then a little bit for the operating system to bring the VM to using just about everything that it's been allocated. The challenging part is that virtual machines with large memory footprints and low active memory counts are usually the first targets for memory reclamation processes if the host is under memory pressure. That means SQL servers are probably going to be the first to start paging if the hosts tell those VMs to start to balloon. Let's take a look at our virtual machine memory statistics, specifically the active memory counter. Okay, go back to your virtual machine, go to Monitor, Performance Advanced, Real-Time Chart Options, go back down to Memory and check Active here, and then hit OK. Okay, we can see in terms of millions of kilobytes, which is very helpful, the amount of memory that has either been read from or written to in the last 20 seconds. If you convert this to either megabytes or gigabytes per second, you can start to get a sense for the amount of activity that your SQL Server buffer pool is dealing with. And now, if you go over to Summary, you can see how much memory that we've got associated, 32 gigs, but VMware is only showing 1.28 gigabytes memory active. In my opinion, that is a completely useless value. You can use an in-guest Perfmon counter to detect if your virtual machine is ballooning. If you're doing any monitoring that can watch Perfmon, you can use the counter set VM memory and the counter memory balloon in megabytes to alert you to see if there's a value there. If it's greater than 0, you run and don't walk to your VM admins and ask them what is going on. We talked about this in the virtual machine configuration module, but if you want to prevent ballooning, simply don't overcommit host memory at all. If you want to guarantee that ballooning will never occur for this virtual machine, go into the virtual machine memory properties and check the Reserve All Guest Memory checkbox. This blocks the memory reclamation processes at the host from ever considering this virtual machine for memory reclamation if it needs more RAM. Double check that your VM admins have not set either a memory limit or share values on the memory. It's very easy to forget about those, and either can cause severe performance problems if SQL Server is unable to access some of the RAM that it thinks it can use for its buffer pool. A share value of anything other than normal means someone has changed the value. Now let's talk about the other major challenge, virtual disk performance. The scenario that I talked about in the storage module is so common that I encounter it on almost a weekly basis. You get long I/O alerts inside the SQL Server and see incredibly high performance latencies from disk. You talk to your storage administrator and they report back that the storage is performing with sub-millisecond response times and that everything is fine. We've talked a lot about the architecture. Now let's talk about the storage queues themselves. Working our way from the bottom of the storage stack to your database, there's a lot of layers to take measurements of performance. At the bottom is the storage disk pool itself. Next is at the LUN on the SAN. Next is at the VMware's data store perspective, and then at the VMware virtual disk. Finally, we get ingest at the OS layer. Believe it or not, you can go one layer further and look at the disk stall rates by database data and log file to get SQL Server's perspective on storage latency. We'll talk about that soon. The lowest layer of measurement is the one you're probably going to have to work with your storage administrators to get access to. Every SAN should have metrics for performance and latency going all the way down into the disk pool. Look for any sort of operational pattern or trend that you can see going back not just multiple days, but multiple weeks. I really hope your storage layer has this level of telemetry available. Most modern storage devices do. All flash storage arrays really shouldn't see spikes greater than 1 millisecond. If you see anything higher than about 3 milliseconds for either read or write, something is probably not right and really should be investigated. If your storage arrays are flash hybrid, I would consider anything above 10 milliseconds as a high threshold for both reads or writes. Spindle-based arrays are certainly slower, and I would consider anything over 25 milliseconds for reads and 10 milliseconds for writes to be high. Just make sure that when you review these values, you're able to split out reads from writes. Now go one layer up and look at the SAN LUN. Repeat every bit of these metrics reviews at each LUN where your SQL servers reside. The numbers should be pretty close to what you're seeing at the disk pool layer. Now take a look at the same LUNs from VMware's perspective. It could be a block-based SAN LUN formatted for VMware VMFS. It could also be an NFS-based mounted volume. Either way, it contains more telemetry for each data store around read and write latency. Just remember that if you're looking further than a real-time view, these tend to be replaced by the highest latency per 5-minute interval values. That is certainly not the same as the 20-second average. Here's where things get interesting. If you look between the SAN LUN and the VMware data store and the performance metrics are a lot worse inside VMware than they are on the SAN LUN, you could have interconnect settings that need to be tweaked or tuned to relieve some of the pressure. The easiest single indicator is if your latency metrics are much higher inside VMware's telemetry than on the SAN for a given LUN. Start by reviewing the interconnects to look for either fabric or networking switch or port congestion, built-in queue depths for any fiber adapters, or things such as receive-side scaling for any physical network adapters. Review the VMware storage adapter queue depths to see if they have both been updated to match the physical device queue depths or just plain too low for the workload that you're managing. Also confirm if active multipathing is configured for your storage presentation to your VMware environment. If you go through the tips that I've presented in the individual modules at each of these layers, you'll find that most of the time we can get telemetry inside VMware to within 1 millisecond of what the SAN is displaying. Next is to review the VMware virtual disk latency metrics. Pick your virtual machines that matter, go into the Performance Advanced pane and select Virtual Disk. You'll have metrics here for both read and write latency by drive. It's listed by its SCSI ID number. You do have these mapped from your virtual machine deployment, don't you? If you see latency metrics here that are much higher than the associated data store, you could have either hypervisor level or VM disk controller level storage contention. Let's take a really good look at key indicators of VMware data store latency. Go to your virtual machine, go to Performance Advanced, and now go Real-Time Chart Options. Or here, honestly, you can just look at the data store drop-down view. And you can see for every data store that you have a virtual disk on, we now have read and write latency metrics. Also notice you can go backwards in time if you have changed the vCenter statistics levels. You can see here at 6 a.m. roughly, something is running. We've got a small spike there. You can see also probably right after midnight, they're probably doing backups or something. We've got a little bit of latency there. This is perfectly normal. When these things really get stacked up, we can start to see delays. Now, if you go to past week, things like that, you can start to see how the granularity becomes an average of an average of an average, and we start to lose the information that we actually care about because that is nothing like what we were seeing in the real time and the past day view. What can you do something about it? Take a really good look at the data store DSNRO. This layer and everything below it have built-in queue depths and other points of contention that we've talked through already. Another layer to take a really good look at is the number and configuration of virtual disks and disk controllers on a given virtual machine. You might have too few controllers with too many objects all piled onto one controller. If you have more available controllers, or maybe they're not PVSCSI or NVMe, consider adding or changing your controller type to improve the queuing at that layer. As with before, continue to verify with your virtual machine and storage administrators that you have the appropriate multipathing from the hypervisor to the storage. If the storage is running slow, the queues can continue to back up further into the infrastructure stack. You can be somewhat proactive in monitoring for these points of contention. In-guest level operating system and SQL Server metrics can be your leading indicator because you are at the end of the chain. Take a really good look at per virtual disk latency metrics at the operating system level. If you see crazy spikes there, start to look underneath it. The same goes with elevated disk latencies inside SQL Server. The same go with I/O-related wait statistics inside your SQL Server instance. The fun part is VMware has an absolutely amazing metric that hardly anyone's ever heard of called average number of outstanding read or write requests. It's collected by VMware per virtual disk for virtual machines. It's a really simple indicator when the hypervisor is imposing a storage penalty of concurrent storage commands. Take a look on the screen and you can see specifically where to select to uncover this buried metric. If you select Advanced Performance and then choose Virtual Disk, you'll see the top two counters are called average number of outstanding read or write requests. Check both of them. On the bottom under Objects for this chart, you'll see each of your virtual disks listed by SCSI ID. You can start to see the number of pending I/O commands per virtual disk over the past hour. If you've updated your vCenter statistics collection, you can see this metric for longer. Take a look at the periods of time where you start to see significant amounts of storage queuing. Every time you see a spike here, your in-guest storage latency is climbing, but the disk pool layer on your SAN is probably just the same. You'll also notice that if things get rather bad, they seem likely they'll have a cap at a value of 1280. This is a cap internal to the VMware kernel that is completely undocumented both publicly and inside the VMware knowledge base. If you call them or ask about why this is capped at that value, they will not have an answer. Take a really good look both at the individual virtual disks that are being bottlenecked on either reads or writes or both. You can sometimes start to find individual disks that are acting as primary bottlenecks to performance. Whenever I see single virtual disks where all the storage is spiked, it is now time to dig into the virtual machine and the database workload itself. Let's see some of this in real life. Go back to your virtual machine, Monitor Performance Advanced, go to Virtual Disk, uncheck everything, and now select the top two, the average number of outstanding read and write requests. On the right down here, you see your target objects. These are each of your virtual disks. Hit OK. And now, check this out. We have the average number of outstanding read and write queued inside the virtual machine here. And there you notice, right at midnight, a value of 1280. That is the value I was warning you about. In this case, I think they're doing backups or something really big, and it was flooding the I/O queue very, very briefly. Through the whole rest of the day, we really don't have any issues here. If you had hotspots during business hours or really critical time periods, this is where you'd want to go look. Now let's take our in-guest disk latency metrics as measured by Perfmon and overlay these with what the hypervisor virtual disk metrics are showing. The counters that I really care about here are under the physical disk counter set and our average disk seconds per read and per write. These values are stored in seconds, so multiply them by 1000 to convert them to milliseconds. If your storage is extremely good, convert them to microseconds. The biggest thing that I want to stress here is that this is one point of view. Please do everything you can to compare these numbers to what you see with storage queuing within the average number of outstanding read and write request counter inside VMware's virtual disk layer, as well as the VMware data store latency layer. If the numbers inside the guest are much higher than what you're seeing at the VMware layer, but you don't see any signs of things like disk queuing or controller queuing, we may have something even weirder going on inside the guest operating system. It could also be concentrated hotspots from within the database engine that we need to start to work our magic to resolve. If we see hotspots here, what can we do about it that we haven't already talked about before the hypervisor layer? We can take a really good look at balancing our virtual disks more optimally amongst our virtual available disk controllers. It could actually be time to take a look at our SQL Server workload. If we have a single database data file that is getting slammed by your workload, now could be the time to strongly look at adding more data files to that file group or even more file groups distribute it amongst more virtual disks and controllers, and start to spread out your SQL Server workload. I know it seems like an incredible amount of work, and you have to make the judgment call at what threshold does this become too much of a pain point for you to be able to ignore. We can only tweak and tune the underlying hardware to a certain point. At some point, we have to take a really good look at the database workload itself to try to more widely distribute its storage consumption. We can do this by analyzing SQL Server disk stall metrics. SQL Server keeps track of its perceived latency while accessing a given database data or log file. There are many situations where SQL Server simply can't get access into the file on the file system fast enough to fulfill a request. In this case, it could just be that the SQL Server storage engine itself has been bottlenecked. We can take a really good look at this out of SQL Server Dynamic Management View, but keep in mind that if you just look at this on the fly, it's the average disk stall rate by file since the last reboot. I guarantee you your workload patterns are not completely identical throughout the day. As we've seen with everything else we talked about, your workloads are incredibly variable. What that means is that we should be collecting snapshots of this metric periodically throughout the day so that we can understand patterns of when there is storage contention on a given database file. This gives us a really good means to look for the hotspots around certain points in time inside these databases. Let's take a look at how we can collect SQL Server disk stall metrics around the clock that we can use to compare and contrast with the underlying operating system in virtual machine level disk statistics. We are going to create a placeholder database, so use any database you've got, DBA database, whatever. We're going to call this table a disk stall table. Server name, instance name, database ID and database name, physical file name, database file ID, average read stall in milliseconds, average write stall in milliseconds. The rest of this is also good information for you. Here's the secret sauce. This is a stored procedure that gives us the difference between the last sample and the current sample of disk stall. We're going to schedule this with the agent to run either once a minute or every 30 seconds or whatever frequency you want, and we've also got a proc in here to clean up after itself after so many days. Feel free to modify all of these. So now we're going to create a job in here to go schedule this. I like to do, honestly, every 30 seconds to a minute. You can see I've got just a normal DBA utility database in here. We're just going to execute the stored procedure that goes and gives us our diff. And then we'll go ahead and run this every 1 minute. We'll just run it around the clock, and that way we've got tons of good information. And then we'll go ahead and create the job that'll clean up after itself. And again, use your best judgment on how long you want to keep the data around for. You may want to keep it around indefinitely in case major things change over time, or you may just want to keep it around for a month or two. It's completely up to you. In this case, we're going to execute this stored procedure that does the cleanup after 60 days. And I'm going to schedule it to run at a very specific odd time in the middle of the night that I know is not going to conflict with anything on this particular server. Okay, now this stored procedure has already had the opportunity to run, so let's take a look at the output. And we're going to see every database data and log file. The fun part is it has now calculated the diff between the last sample and the current sample. Disregard the very first sample because it didn't have anything to compare against. But you'll notice average read stall in milliseconds for both read and write. There's also a lot of really good info in here for number of reads, number of writes, number of bytes read from or written, which I find fascinating because now we can start to figure out the largest I/O consumers of any database in my entire environment. This is where things get even more interesting. If you do have confirmation of hotspots on a given data or log file, but you don't see elevated latency and guessed at the operating system layer or below, we definitely have some work to do within the databases. More data files and potentially more file groups will definitely help improve the situation. This is why we actually create more than one tempdb data file to begin with. Your user databases need this too. Take the additional files and distribute them wider with more virtual disks and improve their distribution amongst the additional disk controllers. If you continue to find hotspots, strongly consider exploring SQL Server table-level partitioning. You don't have to go absolutely crazy with this stuff and have a bazillion different virtual disks and thousands of partitions, but if we have a significant bottleneck here that is not manifesting as underlying platform latency, it is your duty to at least start to tune this to make an improvement. Finally, let's switch gears to virtual network performance. If you find that you have lower than expected network throughput, first use iPerf to double-check end-to-end peak possible throughput for synthetic tasks. I noted how to use this tool in Module 3. If you find that the test results in much lower than expected throughput, work with your virtual machine administrators. You can also check for network packet drops or discards within Perfmon. The counter set is network adapter, and the counters are packets outbound or received, discards, and errors. If you do find anything greater than 0 here, you should look to see if you have some level of network traffic monitoring to help figure out certain devices on the network that are contributing to some of your network performance problems. Another area that I find periodically is that CPU 0 consumption rates could be very high and your network throughput could be quite low, or at least lower than expected. If you simply can't get anywhere near 10 gigabit or above performance, we may need to enable in-guest receive-side scaling. You can do this by editing the virtual machine network adapter settings and go to the Advanced tab. Look for the property called receive-side scaling and enable it. It will briefly disconnect your network adapter, so do not do this during any production hours. Another setting that I could potentially disable, but only rarely have to, is a setting called Windows Network Auto-Tuning. I've only needed to disable this setting a couple of times in my career, so I doubt you're going to need it to come up, but I thought I'd mention it here. The last bit of network tuning to squeeze that extra bit of a fast network demand is to enable jumbo frames inside the virtual machine as long as everything else underneath is lined up. Once you do that, you can increase the SQL Server networking payload size from 4K to 8K. To enable the setting, go back into the network adapter properties and under Advanced, select the jumbo packet property and enter the given value given to you by your network administrators. Usually it'll be 9,000, but they may have a custom value for you. Now we can start reviewing our SQL Server network packet size to see if we can make an improvement here. By default, SQL Server transmits data in a 4 kilobyte payload. Under normal frame sizes, that's 3 frames. By enabling operating system jumbo frames, we can now validate that we can transmit our network payloads at 8K and use just one network frame to transmit a payload. It should reduce TCP segmentation across your environment and hopefully improve performance, especially if you're routinely moving around a lot of data. Wow! I cannot believe we made it through the performance tuning module. Make sure to watch this one a couple of times because there is a ton of information in there. When you're ready, let's go next to the availability tuning module.